Grade 12 Physics, Dynamics, Note number 4, Newton's third law and tension. So this note, we're going to review Newton's third law, and we're going to try and figure out how to solve tension problems that you might encounter in the homework. Newton's third law basically means that if we have two objects, and if object A puts a force on object B, then object B will put an equal and opposite force back on object A. So that's what we can write here. FA on B equals FB on A. This is the idea we use when we calculate tension in ropes. This is where the tension comes from, as the ropes are attached to a wall. Basically, whenever you solve these problems, you want to simplify them by setting up a system of equations based on balanced forces from a single point. And you'll see what I mean when we get into the problems. So here we have our first problem. Let's say we have the following setup. Basically, we just have a ceiling with three weights hanging in a line. So weight number 1, number 2, and number 3. We'll label them as so. Each of them has a mass, so the first one will be 15 kilograms, second one 7, and the third one 13 kilograms. Now the ropes between them are where the tension is going to be, so we'll call the bottom one there, because it's between 2 and 3, we'll call it T23. The next one will be between 1 and 2, so T1 and 2, and we'll just call one on top T1. The idea of solving this is we want to start from the bottom box and then work our way upward. So let's look at the bottom box and draw a free body diagram. Gravity's pulling it down, and then the tension between 2 and 3 is pulling it up. So we know the box isn't moving, so those forces have to be balanced. T23 is equal to mg. So let's put the numbers in. So here we get T23 is equal to 127 newtons. Let's analyze box 2 and draw a free body diagram again. Fg is down. This time though, T23 is down. You can see it's on that side of the box. And then T12 is up. Again, the box isn't moving, so we know all those forces are balanced. So we can set up this equation, sub in our values for Fg. It's only the force of gravity on that box, so that's why it's 7 times 9.8. And then we can solve for 196 newtons. Last box here, again, free body diagram. There's Fg, there's T12 pointing down, and then there's T1 pointing up. They're balanced, so we'll write that down. And sub in our values, so the mass of the box 15 times 9.8 plus 196, that was from our last equation, and we get 343. Notice here, right, as the tensions go from the top to the bottom, they get less and less and less, which makes sense. Okay, next problem here. Let's consider the following system, and what we're going to do is we're going to solve for T1 and T2. So what the system looks like, it's basically two walls that are vertical, and there's going to be a mass hanging between them on a system like so. So T1 and T2. The central point there is the one we're going to want to focus on, and that's where the 52 kilogram mass is going to be hanging from. What we first want to do is we're going to break up T1 into x and y components. So T1 is going to have a vertical y component and a horizontal x component. And now what we want to do, knowing that the system is at rest, we're going to set up some equations of known quantities. Okay, stuff that we know should be balanced. So in the y direction, we know that T1y has to be equal to mg. We'll call that equation 1. In the x direction, we know that T2 has to be equal to T1x. Now, additionally, we can relate T1y with T1 if we know that angle theta, which would be 40 degrees. Here, T1y and T1 is related through cos. So cos of theta is going to be equal to T1y over T1, which means T1y equals T1 cos theta. So if we move that equation up here, and remember equation 1, we can sub that in. So mg equals T1 cos theta. So rearranging for T1, we get mg over cos theta, and we can solve for T1. So here we get T1 is equal to 665 newtons. Okay, now we need to solve for T2. We can do that. We can relate the other side, the Tx, to T1, and that's through sine. So sine of theta equals T1x over T1. So T1x, which from equation 2 we know is T2, should be equal to T1 sine theta. So let's solve for T2 here. T1 was 665 times sine 40. So 428 newtons is our value for T2. Okay, next example. Let's solve for T1 and T2 again. Slightly different problem. This time we have our two walls, but both of the ropes are going to be on an angle. Again, here we have T1 and T2 on different angles, 65 and 50, 35 kilogram mass. We're going to want to concentrate on that central focal point. We know it's going to be pulled down by mg. And we're going to break apart both T1 vectors, so that's T1y and T1x, and the T2 vector, T2y and T2x. So what we want to do here, just as we just did, we're going to analyze that connection point, and then we're going to set up a system of equations using those components. So first of all, looking at the up-down direction, let's set what we know is equal. So T1y plus T2y should be equal to mg. But what are those components? We can write the full form in. So T1y is going to be T1 cos 65. T2y is going to be T2 cos 50 is equal to 35g. Let's look at the left-right. We know that T1x should be equal to T2x. There's no other forces. So writing what those components are is T1 sine 65 equals T2 sine 50. Basically what we have here, we're going to rearrange that for T1. We have two equations with two unknowns. So we're going to use substitution or elimination to solve for T1 or T2. Here we're going to use substitution. So we're going to sub equation 2 into equation 1 to solve for T2. So this is what it's going to look like. This is T1 being subbed into T2. So there's the rest of equation 1. We need to factor out the T2 term from those two terms on the front side. So this is what the factored out version is going to look like. Now we just need to solve for T2, which ends up being 343 newtons. Now all we have to do for T1 is solve for T1 using equation number 2. So putting our numbers in, we find that the value for T1 is 290 newtons. Okay, last example. This one's going to involve an acceleration. So let's say we have a train that's accelerating in one direction. There's going to be a locomotive with 3 cars. We're going to determine the tension between each of the cars below. So there's the picture being drawn. We'll just call the locomotive number 1, 2, 3, and 4 for the cars. So that means we have T12, T23, and T34. Each is going to have a different mass, so 113 tons, 54 tons, 26 tons, and 38 tons. Okay, some more information about the train. The train's going to pull with a force of 65 kilonewtons, so basically that's 6,500 newtons. There's no friction. The conversion for a ton is 1,000 kilograms. What we need to do is first find acceleration, and then again, just like our other problem, we're going to start from the bottom or start from the back and then work our way forward. So finding the acceleration, just using Newton's second law, the acceleration is going to be the force divided by the total mass. So there's the force divided by all of the masses added together. And we find that answer to be 0.281 meters per second squared. Next, again, starting from the back, let's look at a free body diagram for car 4. The only force is going to be T34 that's pulling it forward. So F equals ma for that car. T34 is going to be the only force. M4A is going to be on the back side. So solving for T34, we put the mass in. We found the acceleration, so we'll put that in. We find tension here is 1.07 times 10 to the 4 newtons. Moving on to car 3, free body diagram again for this one. T34 is back, and T23 would be pointing forward. And we'll call that the positive direction, so that means T34 would be negative. So T23 minus T34 equals M3A. So solving for T23, we put our values in that we know. Acceleration comes from before, and T3 comes from the earlier equation. So T23 is equal to 1.80 times 10 to the 4 newtons. Finally, looking at the last tension, we're going to use car 2. So T23 pointing back, T12 pointing forward. So again, we'll have T12 minus T23 equals M2A. Putting in our values that we know. Things that we've calculated from equations before. We finally find that T12 is equal to 3.32 times 10 to the 4 newtons.